Group 22, and our project is based on the producer and consumer paradigm problem. Now, the producer and consumer problem is a very famous synchronization paradigm, as we did cover this topic early in the semester. So, what essentially is we have these producing threads, and then we have these consuming threads, and we have a shared data structure such as a queue here, for example. And the producers, what they do is they produce items inside the queue, and then we have the consumer threads who consume these items. So what we essentially wanted to do is we wanted to emulate this problem. We wanted to explore the real world applications of this problem. So we went ahead and researched some open source tools that would allow us to do this, and we came across this interesting tool called Redis. Now, Redis is an in-memory data structure store, and what it allows us to do is it allows us to create a data structure within memory. So as you can see, if we go back here, this would exactly be the Redis queue in the which would be the in-memory data structure that we would create inside our application. Um, so you see here's the documentation for it. To get us started with this project, we did go through some research, which we went through this feature right here, which is the producer and consumer paradigm in real-time applications, and this paper talks about some of the real-world applications that this can be useful for. And right here, we're gonna go ahead and just demo a small little program here. Now, the sort of applications that you're gonna be seeing throughout the video is we're gonna be doing a video editing, just because video editing is quite a long process. We're doing some web scraping as well and showcase how exactly the producers are able to produce items inside the queue, and they obviously work in a first come first serve basis. And then we have the threads, which the working threads, which take these and process them in the background. Now, Redis Redis allows us to be able to um, view sort of what exactly is going on within our program by this dashboard. As you can see here, I already have five working threads that are currently listening on Q0. And what essentially Q0 does is something very basic. So it just puts the thread to sleep for a brief 10 seconds. So I'm going to go ahead and showcase that right now. So I'm going to go ahead and run the producer main.py. And what this file does essentially for at the moment, it's just for demo purposes of this video, we're going to show how it produces items inside the queue. So right now we're gonna go ahead and produce five items to be in queue. So think of it as this being the user itself would actually be the producer, and then we have already the consuming threads initialized, as you can see here. If for some reason the working threads were were registered to a different queue. For example, if it was registered to a Q1, then that means that the threads wouldn't exactly do anything just because we already had initialized them to be listening on Q0. So I'm gonna go ahead and showcase this right here. So as you can see here, you have select sleep for 10 seconds, and as you can see here, the threads are actually right now working, and right now there are currently zero jobs inside the queue because they are they were working on them, right? So since well, eventually, since they have now are paused, that means that there's nothing inside the queue as all the jobs have been completed. Now, if I keep producing items inside the queue, we will obviously see that these will eventually start working again, and we're gonna see this queue grow inside our in-store data structure memory. So as you can see here, Q0 is continuously growing. You can see here I have queued in around roughly 20 jobs, and as you can see here, these current working threads are currently working in the background, trying to accomplish the task in hand. So you can see here, this just recently was at 20, now it was at 15, now it's currently at 10. Just because it just, whenever a thread it gets done with its work, it keeps consuming. Now, the nice thing about the Redis is that it is thread safe, as we don't really have any sort of synchronization problem. The only problem that we may have is the fact that um, we won't be able to. It's very hard to coordinate the results between each other. So that's actually quite a issue that we've been trying to solve now. So for example, if we were to do some sort of a long computation, it will be very hard to coordinate the results. Granted, the results are posted based on the job ID. However, it does take quite a while for that to get processed inside. So that's something that we're still currently working on. So as you can see here, we have Q0, which is very simple task, and we're gonna have different queues, and these queues each have a different sort of job in place. So, for example, the Q1, it has a job description in place to be able to read a CSV, large amounts of CSV file in one time. And then we have Q2, which does the video editing for us, and we will also showcase how we are able to actually parallelize this work just because we have so many workers, and the portion of parallelizing, the challenge about that is being able to produce the logic to where parallelizing it makes sense. um, so we will see going on in the video how this works, and we'll also explain how the code works for it. So now we're gonna go ahead and show the actual code in action, and we're gonna actually show how Q2 works. Q2's job is to process a video and essentially split it into 5 different videos. So right here would be the sequential version of the code. So as you see here, we get the file location, and then from here it gets the number of frames and the duration of the actual video itself. And then from here, so we do all this right here just to know from where to trim. And then from here we build the command, and we're using ffmpeg, which is a very famous command line interface tool to accomplish video editing. And then from here it goes through a loop and executes these in a sequential fashion. So for example, since this is a 40-second video that we're going to be doing, we're expected, so 40 divided by 5 equals 8, so each video should be roughly around 8 seconds. And we're going to go ahead and see here how exactly how fast this actually runs. So first I'm going to go ahead and run the sequential version, and then after that I'm going to go ahead and run the parallelized version. So I'm going to go ahead and run this one right here, and I'm going to go ahead and taking its time. Okay, so now as you see here, it is currently running. I'll run this version. So as you can see here, the workers are now currently in action, and there's currently nothing inside Q2 just because there are already 5 workers ready to be able to take those jobs. And what I essentially did was I split the the videos into segments where we want to trim, and that's where the logic comes from for doing accomplishing the video editing. So as you can see here, the parallelized version, the parallelized version was completed in roughly 13 seconds, and the sequential version was finished in 27 seconds. So as you can see here, this tool readies and allowing us to be able to have um, multiple workers working at the same time on the same task is quite useful, as we can get the time down quite a lot for it. Um, for if you see here, how Q3 has 5 jobs right now and nothing is going on, the reason why that is because there's currently no workers actually listening to this queue. So that's exactly why this just stays like this. So for now, I want to kind of walk through a little bit of how the logic for this works. So obviously, whenever we start the code, it just asks us what sort of queue we want to listen to. So in this instance, I went ahead and picked Q2, and from there, what I do is essentially I produce the video splitting logic, which is essentially the same code right here. And from there, I enqueue all these tasks right here. As you can see here, we have the keyword enqueue, and we pass in a parameter which is the actual command that we're doing. So the way that our project is currently structured is we have the producer logic, which would go in here, and this is exactly where I'm getting the video edit logic. You can see here, they were both the exact same files, the file location here, and this is exactly where I build a command to execute ffmpeg.
All right, so here's the second real-world application of having this non-blocking data structure for different threads. And so the example here is if you wanted to have some way to parse multiple CSV files for a certain keyword. So here I have a few CSV files, and to demonstrate, I'm going to choose 3 of them and search for the keyword 2014. So I'm searching 3 stock CSV data files, and I'm going to start the consumers, and I'm going to start 3 consumer threads, and I'm going to assign them to Q1. Okay, so now you can see there's the three workers here looking for Q1. Currently there are no jobs, but I will go ahead and start the job. So each of these files is going to be given to one of the workers. All right. So here you can see the output of the 3 different workers. You can see that they are now finished. There's no more jobs, and they found in the first file 252 occurrences of the keyword 2014, 252 in the second, and 253 in the third. So this shows how useful this data structure can be, especially for organizations with lots of data. You can do a lot of searching through to get what you need using these different workers that are looking at this queue.
So this is the third real world application that can be simulated efficiently using parallel computing. In this program, we are web scraping a real estate website where we gather real estate data. You can see the website here. So as you can see, there are three different pages on the website, and the web scraping program goes through all three of the pages to create a data set. We created three different threads, and we assigned each thread to web scrape each one of the three pages of the website. Um, the code for each task that is passed into the threads can be seen here. Um, so producer one, web scrapes page one, producer two, web scrapes page two, and so on. The data from each package is stored into a pandas data frame in the main class, and then the results are printed into the console, which you can see at the bottom. And we can also see the Redis dashboard, which visualizes the queuing process. Ricardo, you want to explain?
Yeah, so as you saw there, the states were currently in working mode, and since the program just executed, they are now in pause mode. So that's why you saw the changes from the play to the pause. And another thing that I want to mention is that Redis has a built-in blocking mechanism, meaning that for example, for Q2, we have there's currently four jobs in there. Now, these jobs are going to stay in this queue because there's no thread being assigned to Q2. So this blocking mechanism makes it very useful and handy to develop with Redis, so we don't have to worry too much about the synchronization problems.
So this paper talk about a model that that introduced the producer consumer paradigm that construct real-time applications that interact with external environment, which is one of the most important features of a real-time system. The system is a dependent system, so it responds to external inputs such as sensors and then process data and then send out the responses to control the overall system. So this is a standard paradigm that models between the two processes, um, producer and the consumer, which we can see right here, process producer and process consumer. And we use a buffer in these two processes to communicate the producer and the consumer together. And the access to this buffer is through a monitor, which is right here, like the function right here. There's two problems to the paradigm is possible on or not. Firstly, would be the producer being external process, which means we can control this producer to wait for the consumer to consume data before the producer produce data. Secondly, using a wait statement in real-time system is not acceptable. So therefore, we can process our system to be periodic and these following characteristics for each computing in order to apply the producer consumer paradigm in the real-time system. Also, we can analyze the model by using simulation with this following framework right here: specification and analysis. With So this framework comes with these two parts. Moreover, these are the two paradigms that we can take a look at for task scheduling. The earliest deadline first algorithm and the rate mono- monotonic algorithm.
All right. For this section, I wanted to take a look at how Redis is used in the real world and application wise. Redis, we already know, is a message broker, particularly of a master and slave relationship architecture. There's many other message brokers that can be used, though. We just used Redis mostly because that's the one we knew how to use. But there's other applications out there like Kafka and RabbitMQ, which have different features depending on what you want. Some of these including the message guarantee system of guarantee of to what level they guarantee a message will be sent. Some check it. Some will try to send a message once. Some will try to send it a couple times. And then some will keep trying until it can. Then there's message persistence, which is when, if the system crashes, if it remembers any messages. The throughput, which is how much stuff is going in and out of the system at once, and the latency, which is pretty closely related to throughput, is how fast messages can be read and written to. And Redis in particular, is one with very low latency. It doesn't try to keep on sending messages. It only sends a message once. It has no message persistence because it's all an in-cache memory system, and that's what gives it such good latency and also, by that correlation, a really nice throughput. And this makes Redis really optimal for a lot of small hardware because it only needs an in-cache memory. It's very small, so it can be used on little small devices that have hardware limits like Raspberry Pis and small like ARM boards and all of those little devices. And it's also used in like the background of social media sites where there's a whole bunch of messages being input at once and needed to be loaded for the user. And then there's video streaming on those sites as well, where if you're trying to load a video, it can choose not to load some messages and stuff, thereby sacrificing that to increase the throughput of the streaming. And these are things that Redis is used for in common world applications. There's even I saw a project which was web scraping sites like Twitter with Redis, and it needed that because of the low latency that Redis provided, allowed for the processing of that load of 5,000 tweets per minute being uploaded to those sites.